Okay, folks, this is problem 25 on the next page on 288. Still the chapter on momentum. Now in this problem, there's a picture on the page that looks like this. What you've got is a package with a mass m at the top of a chute, okay, and a package at the bottom of the chute that's got a mass 2m. They don't tell you the mass, and it's initially at rest. There's no friction, it's frictionless. And the idea here is the height difference. This package is 3 meters higher than the bottom package. It's going to be released, it's going to slide down this frictionless chute, it's going to hit this second package at position 2 here. And what you want to do, and they're going to stick together. The first part of the problem, they stick together. The second part of the problem, part B, they hit and they bounce off each other elastically, completely elastically, so there's no kinetic energy loss. And then you have to find, in that part of the problem, you have to find the speed of both packages after the collision. In this one, you just have to find the velocity of the two stuck together after the collision. Okay, so that's going to be the final velocity that we're looking for here. So part A, final velocity, they stick together after collision. Okay, you have to use conservation of energy and conservation of momentum to handle this problem. There's several different problems like this. You should be able to handle one of those on the test for sure. There's usually one of these on the final exam too, a problem where you have to use both conservation laws, conservation of energy and momentum together. So this is the first one you've seen like that. So, and it's a nice simple one. So here goes. So before anything starts happening, the system has a certain amount of gravitational potential energy, mgh, okay, m being the mass of the object that's higher than the zero level, g, acceleration due to gravity, and h is the height. Okay, they give you the value 3 meters, but let's keep it in variable form right now. So I call 3 meters capital H. Okay, so that's the initial mechanical energy of the system. The final mechanical energy before collision, right before the small block hits the second block. By the way, we can't do it after the collision because mechanical energy is going to be lost in a completely inelastic collision. Okay, mechanical energy will be lost. So we can't, we still need to use conservation of energy, but only before the collision, okay, because mechanical energy is only conserved before the collision. By the time the collision happens, mechanical energy will have been lost, so we won't be able to apply it directly then, but we can before the collision. Very important point. Okay, so the mechanical energy right before the one, the smaller block collides with the larger one will be its kinetic energy. The kinetic energy of the smaller block, 1/2 m v2 squared, where v2 represents the velocity of the smaller block right before it hits the bigger block. Okay, now up here, conservation of mechanical energy. Down here, here's the original kinetic mechanical energy of the system, just the gravitational potential energy of the small block. Now we set that equal to the kinetic energy of the small block right before it hits the bigger block. Okay, solving for V2 now, which we need to do, okay, and I'll show you why in just a second. So solve for V2, the velocity of the smaller block right before it hits the bigger block. Symbolically, it's the square root of 2gh, and that works out to, when you plug in the value of h being 3 meters and the value of g being 9.8. I use 9.8 here because I think this one, yeah, this is a odd, so it should be in the back of the book, is 7.67 meters per second. Okay, so that's how fast the smaller block is going right before it hits the bigger block. From that, we can find its mechanical energy right before, from this velocity, we can find the momentum right before it hits the bigger block. So we can find the initial momentum before the collision. Okay, so the initial momentum right before collision is going to be the mass of the moving block times its velocity, which we just found. Okay, now the momentum immediately after collision should be the same, right? Conservation of momentum. So that's going to be, I'm calling that P3, the momentum immediately after collision. That's going to be the mass of both things together, 2m plus m, times whatever that final velocity is of the two stuck together. That's what we're looking for. So now we're employing conservation of momentum. Momentum before is equal to the momentum after the collision. And so that's mv2 is equal to 3mv3. So now we can solve for v3, and notice m cancels, so that's why they didn't give us a mass. It's not necessary for the problem. We find that v3, the velocity of the two blocks stuck together after the collision, will be equal to v2 divided by 3, and that's 7.67 meters per second divided by 3, which is 2.56 meters per second. Okay, so that's the first part of the problem, part A, and that's the easier problem because now we've got to find two velocities. We've got to find the velocity of both the small and the big block after they collide. So now I'm going to do that. I'm going to erase part of this board and all of this one. I'll be right back with you.